Debatten om kernekraft er for mange forbundet med stor bekymring. Skræmmehistorier, som florerer blandt medier og politikere, har plantet en frygt i store dele af befolkningen. Kan et kernekraftværk blive et terrormål? Hvilke sikkerhedsmekanismer bruger man for at styre en reaktor? Og hvad med sikkerheden omkring affaldet? Hvordan virker et kernekraftværk egentlig? Alt dette og meget mere får du svar på i dette interview, hvor jeg taler med en amerikansk fysiker om netop kernekraft. Efter denne video vil du vide alt, hvad der er værd at vide om kernekraft, og vil være i stand til at navigere i al information, der kommer fra medier, omkring denne lidt mystiske energiform. Velkommen indenfor.
Good evening, Mark Mills. Thank you for joining me once again.
Good evening, and it's a pleasure to join virtually across the Great Atlantic.
Indeed. You are a physicist and a senior fellow of the Manhattan Institute. What is Manhattan Institute?
It's a think tank, so there are such beasts in Europe as well. So think tanks typically here are policy-oriented, quasi-academic institutions, and usually they will lean left or lean right. And some of them lean a long way left, some lean a long way right. But Manhattan Institute is a right-of-center think tank based in Manhattan, and scholars there research and write about everything from crime and education to urban policy, jurisprudence, the laws, and I do the research and writing dominantly on technology issues, computing and the cloud, as well as energy technology. So it's I hang my hat there. I'm also, so your listeners know that, by way of full disclosure, I used to say when I talked about energy issues, I don't have, the expression, I don't have a dog in the race. But
No.
I'm a founding partner in an investment fund that invests in software in the energy business. We're pretty agnostic. We invest across any energy space, whether it's to make, inspect wind turbine blades or inspect oil pipelines. But the investments tend to be heavily biased towards the oil and gas industry because it's the biggest energy industry. It's far bigger than the others.
Sure. So, do you give advice to anyone who wants to listen to you, or
Yeah. Well, some advice is free, and there's an expression called "you get what you pay for,"
sure.
and then I do some paid for advice, so to speak.
Okay.
But it depends on the client. I had a consulting business for a long time where I did advice giving as a consultant to energy companies and to government research labs and that kind of thing.
Okay.
But then I moved into giving investment advice and wrote an investment newsletter for a while as well.
Oh, I see. Today we're going to talk about nuclear energy, because especially here in Europe, it's a kind of big topic when you see this energy crisis. Nuclear power is come up again as a topic in many governments. So let's take first thing first. Nuclear energy. What kind of material do you need for this kind of energy?
Yeah. Well, the short answer is you need uranium. Because the uranium-235 isotope is easier to fission, to split, than and it only occurs at about a 0.8% concentration in nature. So you have to engage in what's called an enrichment process to upgrade the uranium's concentration. But I think let me back up a second. So the nuclear industry is something that I spent a lot of my early career in because, well, I just ended up I was in Canada at the time, and I was working for a uranium mining company. So the material is uranium. And then I got very involved in the debate about the future of nuclear energy. This is some decades ago, and found myself in the United States working for the industry then. It was then what's called the Trade Association for the commercial nuclear industry. And then, like just coincidence, that was the year I started doing that, was the month that the accident at 3 Mile Island happened. So I ended up spending the week of the accident at the site of 3 Mile Island. And then the next 5 years of my life defending the virtues of nuclear energy. I obviously failed in my mission because most countries have, other than China and Russia, have pretty much backed off. France stayed stable. And then about a year after that, I was in Sweden during their referendum. So in 1980, as you probably know, Sweden had a referendum on whether to abandon nuclear energy or not because of safety concerns, because of the accident at 3 Mile Island. It was an interesting experience because it was my first exposure to that debate in that part of the world. And the referendum was very skillfully worded. People could vote to not abandon it or to abandon it 30 years later. So it wasn't like you would shut down the reactors in Sweden in 1980, but the shutdown would occur in 2010. And I think that won. The majority of people voted to shut down the reactors in 2010. Of course, 30 years passed, and you know what happened is that people forgot that they were afraid and they didn't shut them down, which is a good thing. But anyway, the materials you need are essentially the same as for most power plants, like hydro. I mean, a lot of concrete, a lot of steel, because these are typically big. The designs that we build for electric grids are big power plants. They're 1,000 megawatts each, and they and then you of course use specialty metals, zirconium in particular, to make the fuel rods. So the uranium is converted, enriched. So the natural, I think I said earlier, 0.8%. It's zero. The uranium-235 you need is 0.72% or something like 0.71 occurrence in nature. You need to get it up to 3% occurrence in the fuel to do a commercial reactor. So you do what's called an enrichment process. Expensive and difficult because uranium U-238 is basically counting, it's the atomic weight of that particular isotope of uranium. Uranium-235 is only slightly lighter, but it's chemically identical. And you want to separate out something chemically identical from something that's slightly heavier and chemically identical. Very difficult. It's called the enrichment process. So you do that, and you have fuel, which the fuel is in a ceramic-like form. The pellets typically like the size of the tip of your thumb. And then you have stacked the pellets up in a zirconium metal rod that might be, depends on the reactor design, but let's just say 6 feet high. And the tube's the diameter of your thumb, and you have a group of those tubes, and that would be a fuel element. And of course, you put that in water, and what happens is the natural process of uranium fission essentially gets accelerated by the concentration of the U-235. I mean, this going back into the early 20th century, physicists figured out that the uranium atom could be split by hitting it with a neutron. And when it splits, of course, you release famously, maybe everybody doesn't remember this, but it famously releases the highest density of energy of anything known to man. It's E equals mc squared that comes from Einstein. And if you think of what the C is, energy released equals the mass times the speed of light squared. The speed of light is a very big number. It's 186,000 miles per second, or you could do the conversion. It's something in the order of 250,000 kilometers per second squared times. So you don't have to have very much mass when you multiply by such a big number. So the energy released with trivial amounts of uranium fissioning can produce a massive amount of energy. So this 1,000 megawatt coal plant, which would, nuclear plant, compared to a coal plant that might burn tens of millions of tons of coal a year, that nuclear plant literally converts some matter into energy, but countable in ounces a year to produce the same amount of energy. So the appeal of that, you can imagine, the dawn of the commercial nuclear age, this astonishing amount of energy for a trivial amount of material. It's very exciting. People thought in the 1950s and 60s that basically we would build most electric generating power plants using uranium because it was just so much better in terms of land use and material use.
So this uranium, I'm sure you have to dig it up and mine it.
That's right.
Is it abundant in the Earth's crust, or is it like regularly scattered around the Earth, or is it like pockets here and there, or where do you get it from? But what kind of part of the world?
It's like all other metals. It's relatively abundant. It certainly there's plenty of it on Earth. There was a period in the 70s where people thought that there'd be a uranium shortage based on the plans for so many reactors. But by and large, all of these shortage plans or shortage ideas are, based on bad assumptions. So uranium is pretty common. It exists in very high concentrations in different parts of the world. There's high concentrations in northern Sweden and northern Denmark in the granite. There is in northern Canada. There is in southwestern United States. So they're like all mines. If you went looking for copper or lead or uranium, you'll find higher concentrations different places. And then, yes, what you have to do is, like all metals, all minerals, you have to have big machines, dig up the earth, crush the rock, and then do chemical processes to separate, the element you want out of the rock. But it's not a unique. Uranium mining is not. There's nothing particularly unique. The closest analog for uranium mining is probably gold mining. In fact, gold often co-locates geophysically with uranium. In fact, the mine that I visited in northern Canada, just below the Arctic Circle, was a gold, silver, and uranium mine. All three were co-located in the ore.
Heavy elements.
Exactly.
Yeah.
But heavy elements were made by a supernova billions of years ago somewhere in the galaxy. It's really quite remarkable.
Yeah. This uranium, when you get it up from the ground, can you handle it, or is it radioactive already there? Or
so it's always mildly radioactive. It's probably helpful for people to know some radiation physics. And I apologize for doing radiation physics. There's essentially three kinds of ionizing radiation. Heat radiation is radiation. Light radiation, the light that we use to see, flashlights, those are radiators. They're emitting radiation. The photons are invisible light wavelengths, so you can see them. If you make the photons X-ray photons, you can't see them. They can go through things, but they also are called ionizing radiation when it's that energetic, because what that means is that the X-rays, the reason X-rays can cause cancer is that they are so energetic that they damage the cells. They can damage the nuclei of a cell, and whereas light can't do that, right? You can get light bright enough to blind you, but it's not going to, have the same effect. So in the nuclear business, there's three kinds of radiation. There's what's called alpha rays, gamma rays, and beta rays. And gamma is most like X-rays. Beta is in between. You can stop beta radiation. X-rays, you need lead shield to stop, like when you get a dental X-ray. Beta rays you can stop with just a little bit of cardboard. And alpha radiation is stopped with tissue paper. It's very easy. So uranium, the reason you need to know that is because uranium in nature is primarily what's called an alpha emitter. So you can, if you dug up a rock with uranium in it with a Geiger counter, I could tell you there's uranium there because it has a unique signature on the radiation spectrum. But you can hold the rock, and when you mine the rock and concentrate the uranium, you can still hold the uranium. It's not harmful to humans. You shouldn't eat it. I mean, it'd be like saying you shouldn't eat lead or gold. It's a heavy metal poison. But and alpha emitters can be hazardous if they're in dust and you inhale it, because then you're exposing very sensitive tissues in your lungs. So any risk that's in the uranium mining industry really relates to once you're doing the processing and you get concentrated uranium. You don't want to be breathing uranium dust, but you wouldn't want to breathe beryllium dust or lead dust. It's a similar issue, amplified by the fact that it's an alpha emitter. So even a highly concentrated uranium, the nuclear fuel, once it's produced to go into a reactor, you can handle that too. It's not a hazard to hold nuclear fuel.
Okay. So when you get it up from the ground and you start to enrich it, and then you start to split it in the reactor to create this heat. So what kind of mechanism do you use to control the reaction?
So the first thing is, there's a lot of mechanisms to what you can slow. There's like you can throttle the reaction the way you throttle a car engine. You can heat it up, slow it down. You can turn it off, basically poison. You do this what are called control rods. It's pretty obvious where what the control rods do is they soak up the neutrons. Neutrons are what you use. The neutrons are what splits the uranium atoms. So it's important to understand there's a lot of mythology in people's heads, understandably, that if I take a nuclear power plant and something goes wrong, then it can explode like a nuclear bomb. So it can't. It's physically impossible. It's not as if something goes wrong and you don't get things right, there's some chance, even if it's small, of becoming a nuclear bomb. It can't. It's not possible. To give you a sense of why I'm saying that, I would use an analogy. Most people, anybody that knows anything about agriculture, has been around farms, knows that grain silos have explosions every year all over the world. Wheat, grain, any kind of grain. If you get grain dust and aerate it, the energetic value of grain, which is why you eat bread, will actually cause an explosion, pretty violent explosion. It's a chemical explosion, but you get explosion. But once you take the grain and make a loaf of bread, as you know, there's no experiment you can perform to get the loaf of bread to explode the way the grain did when it was dust. So when you take uranium and you make it into a nuclear weapon, it's designed to be a weapon. And obviously you get a nuclear explosion. When you make it into nuclear fuel for a power plant, there's nothing you can do to make it explode like a nuclear weapon. There's no possibility. It's just not in the physics. But if the reactor overheats, you can get overheating. If the reaction runs away because of a failure of the cooling system or a failure of the control system, then you can boil the water off, right? You can get a steam explosion, which is what happened at 3 Mile Island. If you get hot enough, you can split the water. If you think about it, the water gets superheated, and you essentially electrolyze the water. You get hydrogen and oxygen. If that happens, and you get a spark inside the containment building, you can get a hydrogen-oxygen explosion. That also happened at 3 Mile Island, inside the containment dome. But most people's heads are wrapped around the idea that could either be a nuclear explosion, physically impossible, or you get an outcome like Chernobyl, which frightened people for good reason, because the Chernobyl reactor is profoundly different design than any other nuclear power plant anybody builds. It has two flaws that no one does at it was a Soviet era reactor. One flaw is that it uses its moderating blocks, as if you like, graphite. If you get things hot enough, you can light the graphite on fire and get a graphite fire. There's no graphite in a commercial nuclear reactor, but Chernobyl had that. And it has no containment building. So when you see these typical pictures of a nuclear plant, you see these giant, they're 4 to 6 foot thick, steel reinforced concrete wall domes. Those domes can withstand a commercial airliner crashing into them. They're like the class of bunkers that you built in wartime. So the reactor's inside there. So if there's any chemical explosions or steam explosions, they're all contained inside the dome. Doesn't mean you get some leakage, right? You can get some things can come out. So what you have is people get afraid. They think it's going to blow up like a nuclear bomb. That's sort of what happened in Fukushima. I think, my opinion, the government was in error at ordering an evacuation, because the evacuation killed, I forget the number, hundreds of people were killed trying to evacuate in panic mode because they were afraid. But there was nothing that could happen at Fukushima that would lead to a nuclear explosion, or even an explosion that would be visible anywhere. What they were worried about is an accident being serious enough that some radioactivity got out into the air. That's the reason to be concerned, but it's not an explosion. And the levels of radioactivity that come out from that kind of reactor accident, other than for Chernobyl is a unique case, I don't mean to belittle people's fears, but to put it in context, the levels of radiation exposure that you get from the kinds of accidents that are possible are comparable to the radiation exposures you get from medical X-ray procedures. So they're the same range. Obviously, you don't want it imposed on you because you're not doing it voluntarily, but it's not a catastrophe the way it is imagined. So that's a long explanation that when people have in their heads that this is a nuclear bomb and I'm just keeping a lid on, and if the controls fail, I get a mushroom cloud. This is out of science fiction, not out of science fact.
Yeah, many people see nuclear energy as a nuclear weapon, but you should compare it to like nuclear medicine, like MRI scan or cancer treatment or X-rays or similar to that. So you say that the radiation from nuclear, let's say it got out in the air, it will be the same wavelengths as X-ray.
Well, it depends on depends on what's escaping.
Sure.
But it's not so much the same wavelength; it's the same dose. So in radiation, you talk about doses, how much you get exposed to. So it's a very low doses. However, when you split the atom, you get two different atoms, right? And you don't get two atoms that are exactly the same every time. You get a set of atoms that are called fission byproducts. So when you split the atom, you get other atoms, like an atom of cesium or an atom of iodine or an atom of... So those atoms are radioactive. And iodine, if it's a gas, is a radioactive iodine, which we use, by the way, in medicine all the time to do medical tests and procedures. So if you go to the doctor to get blood work done, you'll have radioactive iodine actually injected into your body because it's a way to trace molecular behavior in the human body and image what's going on. But a nuclear power plant can emit into the air in a very serious accident, which is what happened at Chernobyl, a lot of radioactive iodine. So what people, in that particular case, the threat vector is your thyroid cancer. Iodine concentrates in the thyroid, just like natural iodine is. That's why people eat iodized salt. So iodine goes to the thyroid, and if you get a big enough dose, you have some risk of getting thyroid cancer. Obviously, it's not good to get thyroid cancer, but I guess the good news, if there's good news in this kind of story, is that it's very easy to deal with, monitor, and identify. So it's not it's a bad outcome if that happens. It happened at Chernobyl, but it's not the same as the kinds of industrial accidents that happen occasionally over history. It's very contained, very specific.
So a nuclear power plant is like you make some energy to boil some water to make some steam to power a big generator to make electricity.
You're making steam with fission instead of with burning gas, oil, or coal. Right.
Cool.
Yeah.
So the big concern also now with the war going on in Ukraine with Russia, many say that like this can be a target for terror. What is your views on that point of to not consider nuclear energy?
Well, so again, it doesn't really matter whether the nuclear power plant in Ukraine were attacked by terrorists, by Putin's Air Force, or whether it was hit by, an airplane that fell out of the sky by accident. The kind of consequences are all still the same. These are concrete domes that are thicker than bunkers, so it'd be very, very difficult to breach it, almost impossible. It would take a bomb, a nuclear kind of bomb, to breach those reactor domes. So if you're dropping a nuclear bomb on a nuclear power plant, your biggest worry is not the power plant; it's the nuclear bomb. Yeah. And it is true that you could have what I would call a 3 Mile Island or Fukushima kind of accident at that power plant. But the hyperbole that's being thrown around about this, some kind of great catastrophe for Europe, is just silly. It's not Chernobyl. So even the Chernobyl accident, as horrific as it was, had very, very little health effects across Europe. The people that were killed, sadly, were workers, employees trying to put fire out. People who had their health affected were Russian citizens in the immediate community, downwind from the fire. It's an open fire, no containment. So the Ukraine reactor is not Chernobyl. It's very much like all the other Western reactors inside of containment domes. There is no scenario, based whether it's a terrorist or a deliberate bombing by military, that it would cause it to be some kind of massive ecological or human catastrophe. It'd be terrible in the sense the people out in the power plant site that would be killed, and it would release some radioactivity. You could do that, absolutely. But again, the level, we know a lot about radioactivity. It turns out it's very easy to measure. There's a lot known about the biological effects of radioactive elements, and so we don't have to guess the consequences. So it's a pretty, in my view, irresponsible people to talk about potential consequences there of terrorists attacking it in ways that they've been talking about it. Some government leaders have talked in ways that are very irresponsible. The most serious consequence would be the loss of electricity, because it's such a big power plant. It would stress all of Northern Europe very significantly. It's such a big power plant. And it would be no different than any other horrific wartime event in the sense of people in the immediate area being injured or killed, which is obviously horrible. But it's not the unique feature of it. The radioactivity is not an existential threat. And again, there's nothing that a terrorist could do to cause it to explode like a nuclear bomb. So we have either ignorant, and I mean that in the literal sense of the word, or irresponsible politicians and pundits talking about some kind of catastrophe that would happen if we don't keep that power plant cooled properly. It would be an economic catastrophe. It would destroy the reactor. It's a multi-billion-dollar facility.
Sure. So nuclear energy is most likely the energy source to take over for fossil fuels. But for any energy source, there is some kind of waste. What waste does a nuclear power plant produce?
Sure.
And how do you handle it?
Firstly, whether the time it will take for nuclear reactors to replace all hydrocarbons, on electric grids around the world, is going to be very, very long. We have to build the power plants first. and for many applications, for most countries, burning coal will be cheaper, which is already the case, and burning gas. Also, nuclear power plants, at least as we know how to design them, are more difficult to cycle up and down. And, humanity likes to use energy cyclically. So you end up with what we already have, which is, what I call baseload power plants like nuclear plants, operating alongside natural gas plants that could be cycled, and alongside solar and wind farms, because those can't be cycled either, right? So you arbitrage, if you like, all the different sources. But to go back to your question, which is to think about what it would take to.
Oh, the nuclear waste. That's
the
also
waste.
a big topic in the mainstream media about the waste. That's also one politician used as an excuse not to consider it. But is it a big problem with the nuclear waste?
Well, it's probably the least of the problems that nuclear energy has. The biggest problem is perception. To your point, what people think is true that isn't. That's the biggest problem. But as a practical matter, the biggest problem is the regulatory systems in place in most of the world make it difficult and expensive to build the power plants. So that's essentially problem one. I guess the next problem, if you're sort of ranking engineering problems, is that to make them safe enough that people don't have fears once they understand how it works, it's an engineering challenge. It's based on the designs. That's why the designs that exist have what are called inherent safety. Inherent safety, if you think about it, is equivalent of ballistic parachutes on small aircraft. Right? It's some of the smaller aircraft now, for hobbyists and private pilots have ballistic parachutes. If your engine fails, the parachute, and you land softly. It's quote fail safe. That kind of engineering is possible inherently in nuclear energy. The third issue, of course, to your point, is waste. So there's a bit of a misnomer. The word waste in people's heads, usually you're picturing a pipe with a lot of glop coming out of it, or a pile of ash. The word waste has a connotation. So nuclear power plants don't produce waste like that. What happens is that the fuel gets exhausted in its capacity to operate, to fission. You use up something on the order of 20% or 30% of the U-235, not all of it. And at that point, the fission products, these byproducts that happen when you split, they dampen out, they poison out the ability to maintain a chain reaction. So the waste is considered used. You haven't exhausted the uranium. It's still there. You've just used a lot of it, and it's become used fuel. It's called, the technical term for it is spent fuel. So there is no such thing as the waste in the same sense, like coal ash or carbon dioxide. There's no liquids flowing out. And so the fuel, when it comes out of the reactor, when it's used, or it's now a waste fuel, spent fuel, looks exactly the same as it when it went in. It's not ash. It's still a ceramic-like pellet. The difference is when it comes out, it's extremely radioactive and physically hot. You couldn't stand beside it. If you did, it would kill you instantly. It's extremely radioactive when it comes out. But it's a ceramic-like pellet. So what they do is they move them into what look like giant swimming pools to cool them down, physically cool them down, and the radioactivity dies off over weeks and years. At that point, when it's a lot less radioactive and much cooler, you can do one of two things. You can do what's called reprocessing, or recycle the fuel, by grinding up the pellets and removing the waste products, the fission products, and then reconstitute the uranium in a new nuclear fuel rod. At that point, you have created a physical waste because you're dissolving the ceramic-like pellets. So now you have liquids, which you then convert back into a ceramic. So whether you do the reprocessing or recycling or not, the end game is still a ceramic-like object that's radioactive, and it's physically hot or warm. The older it gets, the less hot it is, physically hot. So then you'd want to know two things. What do I do with that? And how much of it is there? So the quantities are really tiny. I mean, if you think about the quantity of waste that we all personally produce each year, whether it's trash going out on the curb or whether it's the amount of waste that power plants have to produce, including solar and wind plants, right? When they're retired, they're waste, right? The glass panels on the cover solar modules are hazardous waste because they contain metals to stabilize the glass, and you can't recycle them. They're actually hazardous waste. The quantities of that are measured in the millions of tons, whereas the quantities of nuclear waste are trivial. Your whole lifetime, if all your electricity came from a nuclear power plant, maybe it's a quantity of, quote, waste the size of your fist, perhaps. I mean, it's that kind of volume. It's very, very tiny. All the world's spent fuel from all the reactors have been running. There's about 110, 120 reactors in the world. If all of those used fuel rods were put in a soccer field, they could all go on one soccer field, and the stack of them would be maybe, 20 or 30 feet high. That's for the whole world. So the volumes are very small, but it's very hazardous. But it doesn't melt. It's not liquid. It can't dissolve. It can't evaporate. It can't migrate. It can't walk. So it's pretty easy to isolate it from human beings. So the plan would be currently is you just leave it isolated at power plant sites, and then later you could put it deep, in granite, bury it. Almost every country that has nuclear power plants has plans and schemes for deep, safe burial. So it's never exposed to humans.
Nuclear energy, we have a lot of, in Denmark, for instance, we had a lot of old coal-fired power plant. Right. And it would be obvious to convert these power plants into nuclear if the politician wanted to. But how long is this process to build a power plant? In France, I read that they can do it like in 5-6 years or so if the political system cooperate. Is that the same case in the U.S.?
Well, the key phrase you had was if the political system cooperates. So, and the political system is not exactly cooperating. The only new nuclear power plant that's been built in the United States in many decades is in the state of Georgia called the Vogel plant. It's a big double reactor, and I think I lost track. It took twice as long. I mean, I guess it's been a decade or more. It was 12 years in constructing it, and it's 2 to 3 times more expensive than originally budgeted and planned. Okay. This is a solvable problem because this is an engineering and political problem. But you can't convert a coal plant to a nuclear plant any more than you can convert a gasoline-powered car into an airplane. I mean, they resemble each other, that they're transportation machines, and they both burn fuel. And a coal plant, makes steam and spins turbines that puts electricity on the grid. But the design and the nature of the turbines is very, very different.
Okay.
So what you would do with a coal site is, if you have an old coal plant, you could decommission it, disassemble it, and using the same land and the same electric grid infrastructure, you could then put a nuclear plant at that location, and you would certainly save some time in terms of the siting, because every country has issues about where people want power plants, and you would save some money with respect to building transmission for taking off but you can't repurpose a coal plant. It's even difficult to repurpose a coal plant to convert to natural gas. A little easier because you can use often the same steam turbines, but you get your heat from burning natural gas instead of coal. But nuclear plants are very, very different in terms of how the steam turbines themselves are designed. And there are nuclear plants that don't use water and steam. They're called gas-cooled reactors. They're operated at much higher temperature. It's a very nice design. And you use helium as your working fluid, so to speak. And it's extremely efficient and extraordinarily safe kind of reactor.
In the future, now they're working on like second generation reactor, like a molten salt reactor, and maybe even later the fusion reactor.
Yeah.
How far are we for commercial use?
So the reactors that are being designed now, actually designed to make them commercial, are all fission reactors, so splitting uranium. As you know, fusion reactors are trying to emulate what goes on in the sun, which is fusing atoms and having the nuclear reaction, the E equals mc squared, comes from the fusion. Fusion is much harder. It's easier to answer that one. No one has built a design or knows how to build a design yet that reaches what you call break even. That is, you get more energy out than you're putting in. So I think we'll conquer it, but it's not clear whether we'll conquer the basic idea of a viable break-even reactor in next year or 10 years from now or 50 years from now. No one knows. And it will be a big deal when the first one does that. And there's been some extremely exciting progress in fusion, but the progress is, again, a long way away by huge factors from actually producing more energy than we put into we have to work very hard to get enough energy to compress atoms to fuse. The fission reactors, however, the reactors that exist today, by and large, in the commercial world, are really big. They're 1,000 megawatts, right? 1,000 megawatts, a really big power plant, whether it's coal or nuclear. It can provide enough electricity for about 500,000 people. Not very useful for small towns, which is why you have transmission lines and you share it. So there are new designs. Probably, if I picked a number, a dozen to 24 new classes of new designs, from the same size as the big ones today to half the size, all the way down to reactor designs that would be small enough to power just a house. Actually, NASA, the National Aeronautics Space Administration here, has designed and is building a nuclear power plant that's what we call kilowatt scale for the Mars missions and Moon mission. So that's essentially the scale you would use for home. Your home is a kilowatt scale. So of all those designs, I think all of them will work technically. In other words, every one of them will meet the test that they'll produce far more energy than you put into them to make the reactor. And so, because we know a lot about the nuclear fission process now. I mean, it's smaller reactors in nuclear submarines, of course, and nuclear powered aircraft carriers. Those are highly specialized and very different, but the physics is similar. So that technology applied across a whole set of different designs, from molten salt to thorium metals to high temperature gas to modular reactors to tiny reactors. There's a whole array of designs. I think in the next 5 years, maybe roughly, that means that kind of time frame, we'll have a pretty good idea of the 1 to 2 dozen new designs, which ones have the best chance of being commercially useful. I think they all work. Like every one of them, all these designs look to me like they're not aspirational or silly. Then the big hurdle will be which ones, you have to build them to find this out, which ones work well and are relatively easy to build with the infrastructures we can imagine expanding. And once we figure that out, which won't take that long, we can do that in a year or two, then you have to have a regulatory system somewhere in the world where people will let you build them relatively quickly and use them. And I think that's where we get back to the conversation we had earlier about people's misperceptions and fears.
Yeah.
I mean, these will be reactors that have only one failure mode. They don't work or they work.
Yeah.
I mean, they can't explode. They can't have gas. They'll work or they won't.
Thank you for your time. It's been a pleasure, and have a nice day.
Thank you very much. It's good to talk to you, Ricky. Take care.